Greetings. So under embedded microcontrollers, we'll see two topics. One is RISC and RISC. Another one is Microprocessor Architecture. Part 1. So what is RISC and what is CISC? RISC is Reduced Instruction Set Computers. CISC is Complex Instruction Set Computers. Under RISC, the instructions are simple and again it can be performed little faster. So you need around only one clock cycles to be completed, and the control unit is the one which produces the control signals. That hardware part that is used in the RISC is also very simple because it has to produce only simple operation. And in the code size, when you have any program that is written using simple instruction, and again that you may need a large amount of instructions to complete a task. So that means the amount of memory that is required will be large. Otherwise I can say more number of instructions are needed. So some examples are ARM, MIPS and PowerPC. Whereas in case of a complex instruction set computers, the instructions are complex. It means that each instruction will execute more number of operations. So the time taken to complete one instruction may be large, and the control unit that is producing the instruction control signals is also complex. So when you have each instruction which is performing very complex operation, the size of the memory to complete a task will be lesser because each instruction can perform complex operation. So a lesser number of instructions are enough, or otherwise fewer instructions are enough to complete a task. Some examples what you need to remember under the CISC is Intel 86 and AMD. Going into the architecture of 8085 processor, which is said to be an 8-bit processor. This is a famous 8-bit processor. So what does it mean? It can process 8 bits at a time. So this has got address lines, 16 address lines and 8 data lines. Address line, the lower order address lines and the data lines are multiplexed together. To the right end you can see here you have some terms as AD0 to AD7, and the higher order address lines are AA to A15. So you should understand that once the processor has found the register from where the data has to be read, the address lines are no more used. So it can give space to the data lines. Since you have only 8-bit data lines, 8 address lines and 8 data lines are multiplexed together. That means that the lower order address lines and the data lines are multiplexed together. So when the processor executes an instruction, at the early part of your instruction execution, the address lines, data lines are multiplexed together. Once the memory is selected or a register is selected, you will have a signal called as ALE, that is address latch enabled signal, which will separate the address and the data lines, or otherwise which will demultiplex the address and the data lines. And you can see an arithmetic logic in it. You can see the accumulator, 8-bit content from the accumulator and 8-bit content from the temporary register comes in, and after the execution the 8-bit data is stored back into the register or else into the accumulator. So looking into the part by part of architecture, remember this 8085 architecture is fabricated using NMOS technology, and it has got an 840 pin chip. So this will be operating with a power supply of plus 5 volts and a clock frequency of 3 to 6 megahertz. It has got 16 address lines and 8 data lines. With 16 address lines, this can access of about 64 kilobytes of memory. So to make you understand, I can say it's about 2 power 16. With 16 address lines, the amount of memory that can be accessed is 2 power 16. So 2 power 16 is nothing but 2 power 6 into 2 power 10. 2 power 10 is 1024. It is approximated to 1K. So 2 power 6 is 64. So you have a memory of about 64 kilobytes of memory. So kilobyte, it means it has got 8 data lines, so it means 8 bits at a time, so it's kilobyte, capital B, KB. And coming to the accumulator, you can see as I've shown in you in the diagram, accumulator is said to be as a register in 8085. This plays a very important role in execution of instructions. You have to understand that 2 inputs has to go into the ALU, and 1 input must be from the accumulator. Nearly 99% of instruction deals with having one data inside the accumulator and another data coming from the register or any kind of instruction. So the execution will be done in the arithmetic logic unit. And to the diagram at the beneath, you can see here you have some kind of registers. This registers with what you find inside a processor, you call it as a general purpose register. So this is a normal case where you will be studying seeing the term called general purpose register. General purpose registers are registers which you find inside the processor. So here in 8085 processor, you have a general purpose registers like BC, DE and HL. Each registers are individually 8-bit registers, or otherwise they can be used in combination as 16-bit register. So this can store 16-bit data or an 8-bit data. And coming to the program counter, this is again another register. So when the processor is executing the instruction, before one instruction gets completed, the processor will be incremented, the program counter will get incremented, and it will be pointing to the next instruction that has to be executed. So only then the processor can access all the instruction fast, and it can complete the instructions quickly. So that is called as a program counter. So program counter is a 16-bit register that holds the instruction to be executed. And you have another term which is called as a stack pointer. Stack pointer, you should understand, stack is nothing but is a part of a memory. So it's a temporary memory, and again all the necessary data the processor can store. So that location has to be pointed by a pointer, or otherwise the address of that location has to be placed in a register. So that register is called as a stack pointer. Okay, it's again a 16-bit register. So whenever you come across some terms like address, please remember you have 16-bit address lines. So you will have the register size also will be 16. So coming to another register which is called as a flag register. Flag register is otherwise called as a status register, or it reflects the result in the accumulator, or else after the execution of arithmetic and logic unit you will have a result, an answer. Based on the answer, the flag register flip-flops will be set and reset. So you can see something which is called as a CY. CY is a carry bit. So when you add to 8-bit of data, so the answer, if it is an 8-bit, you can call it is of no, you do not have a carry. So the 8-bit data, you are making an operation of 2 8-bit, and the result is also 8-bit, so no problem. But if you have a 9th bit additionally, you will have a carry flag that is set. So in D2 you can see something which is called as a P bit, or otherwise called as a parity bit. So here the parity bit will be set when the number of bits in the answer is even. So when you do some arithmetical operation, you will have a result of 8-bit. So if the number of ones in the register or in the result is even, you will have a parity bit that is set to 1. You have another bit which is called as an auxiliary carry. So auxiliary carry is it's mainly with 4 bits. When you have a carry from the 3rd bit to the 4th bit, you will have an auxiliary carry flag that is set to 1. And you have another flag called as a 0 flag. So when you subtract 5 minus 5, your answer will be 0. So such a kind of instructions you'll have when the answer is 0, the 0 flag will be set to 1. You have another bit which is called as a sign bit. So remember, when you have an answer, the sign bit will represented in the most significant bit. So if the most significant bit is 1, you will have a D7 bit as set to 1. If the most significant bit is 0, you will have the D7 bit as set to 0. So this is a flag register. It's a famous 2-mark question. You have another register which is called as an instruction register, which will hold the instruction, and you have some other register which is called as a temporary register and ALU. So the remaining part of your 8085 processor we'll see in the next class.